Okay. Does it show?
Yes.
Okay, great. So
Yep.
I'm going to just recoup a little bit what we did last time. Last time we had this example where we had a data set that could be perfectly separated by in a line. So I mentioned that and in this case the we couldn't find a solution without regularization. So the gradient descent sequence, either just the gradient descent or Newton, does not converge in that case. So I mentioned that is a general phenomenon if your data set is linearly separated. So if you have a data set where you can completely separate it by some hyperplane, then the unregularized gradient descent sequence will not converge. And so I just wanted to show that this is a general phenomenon. So let's just go over this. So if we have an affine hyperplane, so that's given by some equation. It's a set of all x's in RD. So and vector in RD or point in RD can be described by its coordinates x1, x2, and up to xd. And the hyperplane is then given by an equation. Their coefficients beta 0, beta 1, and so on, such that this expression beta 0 plus beta 1 times the first coordinate plus beta 2 times the second coordinate and so on is equal to 0. So the hyperplane is a set of all vectors in RD satisfying this equation. And so if we have such a thing that completely separates the data sets, so here's an example. Here we have the red ones are labeled -1, the green ones are labeled +1, and they're completely separated by a line. A line is a hyperplane, affine hyperplane in R2, so they can be described with this equation here. So this is where D is equal to 2. But so I want to show that in this situation, there is no minimum for the loss function. So in general, let's assume we have a data set that is totally, that can be linearly separated. So this means that the points which have label +1, this expression here will be positive, will be bigger than 0. And for those points where the label is -1, this expression here will be negative. And that's simply because if you look at the logistic function, right, that is bigger than 1/2 when this expression here is positive, and it's smaller than 1/2 when when it's negative. And that's how we separate points using logistic regression. We look at this logistic function applied to beta times xi, and the logistic function, if that's the value of that is bigger than 1/2, then we label it +1. If it's smaller than 1/2, we label it -1. And that corresponds precisely to this expression here being positive or negative. So that means that what we have is that for all the points where the label is +1, this is bigger than 0. For all the points where the label is -1, it's negative, it's less than 0. So that means if we take this expression and multiply it by yi is +1 or -1. And when yi is +1, well, that's when beta times xi is positive. And so yi is times this beta dot xi tilde here is also positive. If yi is -1, well, that's when this expression here is negative. And so -1 times the negative thing is positive. So in any case, this means that this expression is always positive for all the data points.
Sorry, can I interrupt for 1 minute?
Please.
Yeah. So in the above 2 lines where we have beta dot x tilde, when it's greater than 0, I remember in the last slide, we said that this belongs to H plus, and when it's less than 0, that belongs to H minus.
Exactly.
And H plus was was linked to +-1 and H minus was linked to +1. Why in the last lecture we had this flip notation?
I don't know. It's a good question.
Right.
Let's see here. If this is so, it's 1 divided by 1 plus sigma of minus this thing here. So this is yeah, no, that's yeah. No,
This should be
this is
+1.
correct here.
This is correct, I think.
This thing here is correct.
Yeah. Okay.
Okay, so the loss function, let's remember that what that was, there was this script L of beta is -1 over n. N is a number of data points. And then the log of this logistic function, sigma, of yi times beta dot xi. Now, let's suppose we scale beta by some number bigger than 1. So if you just multiply it by something bigger than 1. Well, because it's yi beta times xi is always positive, you multiply it by something bigger than 1, well, then you make it larger. So that'll be larger than this one. So scaling it by something bigger than 1, they'll give us something larger. So that means that when the logistic function is an increasing function, the log function is also an increasing function. So log of sigma of this scaled thing here will be bigger than the original thing, right? So if you multiply beta, you make beta larger, then the log of sigma of this thing will also be larger. So, well, it's a minus. There's a minus in front of the loss function. So if these things are larger, then minus of them will be smaller. And so this means that the loss function of the scaled scaled beta, so mu of beta, is less than the loss function of beta. And so you can see that the loss function will just keep increasing because, of course, you can multiply by larger and larger mu here. So the loss function will just be decreasing forever. And so there's no minimum. It can't be. You can also see if you look at the gradient here, you can see that that will go to 0 because, again, minus yi mu beta, well, that will be negative, and so sigma of this thing here, as this goes to minus infinity, sigma will go to 0. So this gradient here will go to 0 at infinity. So when mu times beta becomes infinitely big. So it doesn't have a minimum because it keeps decreasing, and its gradient vanishes only when mu times beta goes to 0. So it goes to infinity. Sorry. So that shows that you won't have a minimum for the loss function when the data set can be separated. So that's a general fact. So of course, if it's not perfectly separated, well, then there will be points where these things here do not, where this condition here does not hold, and so in that case there'll be positive and negative, and so that will turn it into a different situation where there is a minimum. So yeah, so you'll not find a minimum if you don't put a regularization in. If you put a regularization in, well, then you limit the size of beta. So you can't scale beta forever. You have to stay inside this thing that Adam drew last time, a ball or a ball in RD, and you have to stay inside of that, so you can't scale beta forever. So that was just
So again, one question. So this loss function which we derived, I thought this is derived for any kind of data set where the output is in terms of 2 levels, like label 1 and label -1. and then this is the what we got. So,
yes.
But we did never put a condition that whether they are completely separable or not separable.
No. I mean, if they're so this shows that if they are separable, then the loss function will not have a minimum. So we can't solve the problem without regularizing it, because the minimum of the loss function will be at infinity.
Right. So my question is like, what in that previous slide was showing that this only if they are separable, then this does not have a minimum, because I thought this loss function is a general loss function for any.
Yeah. No, but the thing is that, so what you have is that if it is separable,
yeah,
you have this condition here for all data points.
Oh, I see. Okay.
You only have that if it's separable.
I see. Okay.
So if it's not separable, then you will have some where this is positive, but you also have some where it's negative.
Correct. Oh, I see. Okay.
So that will change